Good afternoon. My name is Sean Breckling, and I'm a numerical analyst. Numerical analysts are interested in computing and approximating things. For example, a circle contains more information than you can hold on any computer. So someone like me might come along and say, just use a polygon. And if you want a better approximation, just add more sides. That's good enough. Honestly, that's exactly what we bring to more complicated problems in mathematics, physics, finance. I happen to work in fluids, and fluids are modeled often by the Navier-Stokes equations. And the Navier-Stokes equations are famously difficult. In fact, you can't solve them by hand in general. It's just not possible. So you need a computational touch. And even that is actually still difficult because you see this nice smooth flow here? That's called laminar flow. Easy. But this more busy section in the middle, that's called turbulent flow. And for practical purposes, like a plane in the air or a boat in the water, the scales at which this stuff is happening is so small that to resolve it, even on a computer, requires more power than we have. So someone like me might come along and suggest, why not use something called a large eddy simulation? In particular, you could use the one I'm studying, which is called the Navier-Stokes alpha model. Now, what a large eddy simulation does is it looks at the physical settings of the problem, and it does begin to compute an answer, but in the process, it smooths out the smallest details of this while preserving the biggest features of the flow. And this is important because that's where all the important information is in the flow. It's where all the energy and force of the flow is contained. In particular, my model in the discrete settings when we're doing simulations is very good at preserving things like conservation of mass, conservation of energy, conservation of other things you've never heard of like helicity and entropy. It's very good at all this physicality. And what I have here is a direct comparison between two simulations. One simulation does a good job of preserving all this physical information and one does not. And what the result is when you try to infer information about flow, like calculating lift about this cylinder, you get a discrepancy. And a discrepancy that large can blow the wing off an aircraft in a professional setting. We're not interested in that. I'm interested in developing easy-to-compute models like this that are more physically accurate because things that I develop end up in software for engineers, climate scientists, and we're always on the hunt for better, faster algorithms. Thank you very much.